Welcome, everybody, to the March 2024 SJAA imaging meeting. And tonight we have Francesco Meschia and maybe a couple other people going to discuss the Jupiter Deflection project that was started by Don Bruns. And take it away, Francesco. Let's hear.
Thank you. Hi. All right, Jupiter Deflection project. What is this deflection? Well, of course, it's the deflection of light. And as we are all nowadays familiar with the concept of deflection of light because we have seen those beautiful images of lensing of remote galaxies by slightly closer galaxies, creating all those strange shapes and arches. But the deflection of light is actually something that it is often said that it was predicted by Einstein relativity, which is true, but it's also true that it was predicted also by Newtonian gravity. However, the amount of deflection was different between the prediction of from Newtonian gravity and Einstein's prediction. And also the reasons are completely different in the two theoretical interpretations. So this is the reason why in the first 20 years of the 20th century, after Einstein's paper in 1915, there was a lot of interest and a lot of pressure for scientists and astronomers to confirm one of the two theories and see which one was correct. And we're talking about 1915, so World War I was raging in Europe, and it turned out that it wasn't possible to set up an experiment and carry it out until 1919, when Arthur Eddington managed to confirm that Einstein's predicted value was the one that he actually observed using the sun's gravitational field during the total eclipse of the sun. There are a number of very interesting historical accounts of these events. Don has actually repeated the Eddington experiment in 2017, and is going to repeat it again in the upcoming solar eclipse. But with modern technology, is a completely different ball game, I would say. I remember the first time I read about the Eddington experiment and that the deflection that they were measuring was less than 1 arcsecond, and I was still in high school. I thought, how is it even possible to measure something like that, less than the resolution of a telescope that these people were probably able to carry to their to the eclipse site. The interesting thing is that in the project that Don coordinated, we were actually trying to measure something much smaller than a few tenths of an arcsecond, and as we will see in the rest of the presentation. So, okay, this is the deflection part. What about the Jupiter part? So it was actually Einstein himself that had suggested that without waiting for a solar eclipse, it would be possible to experimentally verify the deflection of light using Jupiter's gravitational field. However, the deflections that you can expect from Jupiter are about 100 times smaller than what you get with the sun. And so this became a double challenge. First challenge is that you need to wait for the right opportunity, because not always Jupiter passes sufficiently near a star to produce an appreciable deflection, but also technological, because in 1919 they certainly had no way to measure deflections that were in that order of magnitude. But in October 2023, the opportunity presented itself, and finally it presented itself at a time when the technology that we have available as amateurs supports this effort. So it was technologically and physically possible. And the picture that I have here shows in a planetarium program shows a conjunction that happened in the night between October the 27th and October the 28th in our time zones between Jupiter and one star that is listed at number 93016 in the Smithsonian Astronomical Observatory catalog. This star would pass at just 48 arcseconds from Jupiter, just a mere 20-some arcseconds from Jupiter's limb, so 48 from the center. And this makes it possible to hope to take this measurement. And a previous conjunction of Jupiter, similar to this one, occurred in 1929, so 10 years after the Eddington's experiment, but there was no technology available for this type of measurement. If we want to wait for the next one, it will happen in 2016, which means that this one is essentially a unique opportunity in a lifetime. And because of that, Dr. Bruns published a call, I would call it like that, in Sky and Telescope last summer. I received the electronic version of Sky and Telescope, so I read it in the September issue that came out in late July. And so when I read this, I immediately sent an email to Don, because also Sky and Telescope had botched the link that would have brought me directly to the project website. And so I asked, so can I help? Is it something that would be possible with the kind of equipment I have? And Don was very welcoming and said, yeah, it is actually possible, even with a small refractor like the one I have. And if you can get a resolution, an image scale of about half an arcsecond per pixel, there's a good chance that you can make this measurement. And so I joined the project, and it was not just me from SJAA. We had other three of our members, so Richard Seneger, Jonathan Lawton, and Nicola Nikolov. And we had different fortunes, and there was some people had clouds, some people had some technical issues, but we managed to collect the data and send them from the Bay Area to Don, and who analyzed all of our results. So the conditions in October.
Francesco, can I ask a question?
Please.
So it seems for I don't know why it feels this way, but it feels for me hard to believe that it won't be for another 80 years that Jupiter passes near another, I assume, star of a certain magnitude.
Yeah, so these are 7th magnitude stars.
So yeah, what's the constraint? Like if you had a 15th magnitude star, you couldn't do this, or?
You can, but your signal to noise ratio becomes definitely marginal, maybe too low to make measurement. That said, I mean, in 1929, it wasn't even thinkable to do this, and maybe there will be advancement in technology. I think that Don wanted to say something here.
Yeah, one other unique thing about this arrangement is the stars are all in a row. They're all lined up together. So there are sometimes every couple of years a bright star, but there's no other stars that are in a nice pattern. And that's what made this really unique.
Oh, so you're making the measurement of one star relative to the other stars. So you need a group of stars to do this. Okay.
Yeah, these are differential measurements.
Okay, got it.
Yeah. So the maximum, the closest conjunction happened it was actually on October the 28th at 7:15 a.m. UTC, which for us was 11:15 p.m. of the 27th. There were SAO 93016 was just 25 arcseconds from Jupiter's limb at that moment. And in that moment, the general relativity prediction is that the bending of the starlight by Jupiter's gravity would be just 0.0085 arcseconds, which is like saying 8.5 milliarcseconds. This is the equivalent, it's the width of an article printed on the front page of the New York Times when observed from San Francisco with a paper in New York City. So it's really, really small. So how do we measure 8 milliarc seconds? Well, we do it differentially, which is what made this particular event interesting. We can measure the baseline between the distance, the separation between SJAA 93015 and 93020, which we call top and bottom. So this is what we call in the project the T minus B distance, which is basically not affected or affected in a very minimal way by Jupiter's gravity. It's orders of magnitude less of what you get for 93016. Then you can express the separation between 93016 and 93020 as a fraction of the top to bottom distance. So the center to bottom distance will be a certain percentage of the top to bottom distance. And we expect that this percentage will change during the night as the conjunction becomes closer, and then as the conjunction becomes wider after the closest approach. But even then, how do we do this? How can we hope to measure this separation with an uncertainty of just several milliarc seconds if we have a much larger uncertainty is in the same order of magnitude of the measurement? It basically makes it hard to distinguish the actual data from the noise. Well, the answer lies in the statistical analysis of large data sets that we have collected during that night. So this chart is each of the points. There's actually 2,000 points in this chart, represents a calculated separation of between C and B at different times along about half an hour. Now, as you can see, that there's a dispersion of measurements. The measurements are spread out with I would say, peak to valley is slightly more than 1 arcseconds. However, we can calculate an average value, which in this case it could be 410.455 arcseconds. And there is obviously a standard deviation associated to this average value, which in this case, I asked Excel to calculate it, was 0.22 arcseconds. However, if we want to, if we consider the error that affects the average measurements, that is not the standard deviation. It's a standard deviation divided by the square root of the number of degrees of freedom, which is essentially the number of samples minus 1. If we do the math with this particular run, I actually measured something which is incredibly affected by an incredibly small error, 410.455 arcseconds with only 5 milliarc seconds of uncertainty. Does this mean that through some magic, my telescope had acquired a resolution of a...
Of course, only if they're independent.
Only if they are independent. Hopefully they are.
Well, there could have been, like your telescope could get pushed a little by the wind for half an hour, and what I mean.
Yeah. Well, no, you're right, but they should be pushed also differentially between
okay, differentially, that helps you.
Yeah.
Oh, okay.
Affecting C minus B, but not T minus B. Yeah.
Right.
Can I ask a question? It's just it seems to me this is very similar to exoplanet work, where you would look for deviations in exoplanets, and I'm wondering if that's the same software. I tried to do this once, and what Hai said sort of happened to me is my variance would fluctuate essentially with scintillations of the humidity that would be coming through the Bay Area, so that it was very hard to do exoplanet work, even if you think you've got a good setup. So I'm very interested in see how it turned out, because down in the bowels of Silicon Valley where I am, it was pretty tough to do this, because my standard deviations and all that didn't look good at all. you know, so.
Yep.
Is this the
Seeing
same
the-
software as is used in exoplanet work, or is this?
No, this is actually software that was developed specifically for this
project,
effort
I see,
by
okay.
Bill Fisher.
So maybe it's a whole different set of math. Anyway,
I think probably the math is not that different. It's we had a different set of challenges because I think that with exoplanet work you are measuring the brightness of the change in brightness of the star system,
right.
whereas we were not particularly interested in the brightness, but we really needed to
Look at the
zero
distance.
in on positions and
Yeah,
separations.
if the brightness
Yeah.
stays constant, that's an advantage, because
Yeah.
the brightness would vary with the scintillations, and
And of course,
as vagues as waves of humidity would come through, you could see the brightness change. You know.
Yep.
Anyway, thank you. That's a good clarification.
Thank you. But consider that the spread of those blue dots, that's entirely due to seeing, essentially. And so it's the same phenomenon that you were observing. We just were interested in different parameters. So, rhetorical question, does this mean that my telescope has a resolution of 5 milliarc seconds, or even just a 0.22 arc second? It's a 5-inch refractor. No, of course, it does not mean that. Because first of all, resolution, if we're talking about image resolution, is dictated by optics, and it affects the point spread function of each individual image, and not directly the positional uncertainty. What we have here is that 0.22 arc seconds is the expected spread around the mean of each new measurement. So every time that I take a measurement, I have a 68% probability of finding it within one standard deviation, so 0.22 arc seconds from the mean value. However, 5 milliarc seconds is the uncertainty on the value of the mean if I consider the entire population of samples in this 30-minute interval. So we're not reading the article on the front page of the New York Times, but we hope to be able to tell if the person moved to the side, and by looking at how the image of the newspaper shifts. What do we need to take this data? So Dr. Bruns actually suggested that the optimal setup was to strive for an image scale of about half an arc second per pixel, which happens to be the resolution that I get. It's actually 0.53 arc second per pixel is the resolution that I get with my 5-inch refractor at its native focal length with my camera that is an ZWO ASI 294, which has very small pixels, 2.3 microns. And so that was good for me. I didn't need to get any special equipment for this experiment. You also need to have an exposure duration that is long enough to collect enough light and provide a good signal to noise ratio. So if the stars were much dimmer, we would need to use a longer exposure time, and so we would be able to fit fewer samples in a few hours of data collection. But fortunately, we didn't have this problem, and we could actually image with the stars without saturating them. This was very important if you want to make this centroid measurements. We were able to reach that with exposure times between 5 and 1 second. So that was pretty fast. This also means that you have to use a similar technique as the one that is used by people that do lucky imaging. So you have to take an uninterrupted stream of exposure with fast readout times, minimal delay, and store everything on the hard drive and for later analysis. You don't want to tie up your CPU during analysis while you are taking the data. So you set aside and then analyze. Don actually had given an excellent suggestion that if you rotate the camera 45 degrees, you're going to have the 3 stars that happen to be almost in a line that will be approximately horizontal across the sensor. So you can actually instruct whatever is your acquisition program to capture only a small region of interest. And so you get quicker readout and very importantly, small files. Because the first time that Don suggested that I should do some preparation work and try to take 10,000 frames and see what is the kind of spread that you're getting. I was thinking, okay, 10,000 frames, each frame is 90 megabytes. So it's gonna take a huge amount of space. But yeah, he then pointed out that I can use a small region of interest. And actually each file was just a couple of megabytes. Each FITS file, just a couple of megabytes.
Hey,
So the entire data. Yep.
What's the advantage of the short, the 1 second exposure? So why not take a 5-minute exposure? Well, if you didn't have to saturate it, if you didn't worry about saturation,
it's the problem is that you're gonna take fewer exposures in the observation window, and so when you try to calculate the uncertainty of the mean, remember you have to divide by the square root of the number of degrees of freedom.
Yeah, but I would have thought n has to do more with photons than with.
No, it's the number of samples in the population. Yeah.
All right. Well, I'll. You have in theory. I won't push it too much, but if you had a 5-minute exposure, not worrying about saturation, you probably have a better, estimate of position than if you take a 10-second exposure, I would think, if you're computing the centroid. So you are getting some benefit. You don't just throw away, you know what I mean?
Well, I would argue if you don't saturate in either of the two cases, it means that the signal to noise ratio is similar in the two cases. You get roughly the same number of photons. And so there is an advantage of taking more, not a long exposure time. You let seeing blur your image over time, and you don't have the advantage of having many samples to reduce your statistical uncertainty. I think Don wanted to comment as well.
You're on the right track that you want to capture as many photons as you can. If you had like a 10-second or 20-second exposure, you'd need a filter or something so you don't saturate and you're losing photons. So basically, this is real nice. It is about 1 second or half a second, and that was long enough, and you got lots and lots and lots of images. Turbulence averaging doesn't really matter because you're looking at very short snapshots anyway, and you're integrating all of the exposures, all the photons, the turbulence will average out. So basically, we got lucky that it's about the right exposure.
And we essentially divided the data in blocks of 30 minutes. And in every 30 minutes, I was collecting 2,200 individual subs. So yeah, there was a lot of data. So what can you expect when you embark in a project like this? What does the conjunction look like? So this is a frame from the data taking, and I labeled the stars and the Jupiter satellites. But essentially, what you can expect is to have to collect about 4,000 images per hour, and in each of them, you're going to have Jupiter's image that will be completely saturated. There's no hope of recovery, and we are not even interested in recovering it. Jupiter's satellites, the Galilean satellites at least, will also be saturated, but you definitely don't want to approach saturation. You need to remain in the linear range for the 3 stars, not because you are doing photometry, but because you need not to be you need to avoid saturation for the sake of being able to calculate the centroid of each light distribution around the star. And this is very critical. We found that this depends, the goodness of measurement depends very heavily on this. And there's another thing that you may want to notice in on this image. There's a very distinct radial gradient around Jupiter, and this came back to bite us, and we'll talk about that in the rest of the presentation. So once you have these 4,000 images per hour, how do you do data reduction? Well, the first thing that you do in a nutshell, you extract the celestial coordinates of the 3 stars from a trustworthy database, and we use the Gaia. Gaia's positional accuracy is down to 25 micro arcseconds, so it's plenty enough for our use. And then you use a tool developed by the US Naval Observatory. It's called NOVAS. It's actually a library in Fortran of all programming language. And it's used to convert the celestial coordinates to topocentric coordinates. So basically referred to your particular position on Earth as an observer. This is important because when we try to measure thousandths of an arcsecond, differential atmospheric refraction, one star is higher and one star is lower, is definitely a thing, and it's going to affect your measurements. So you need to have Don prepared a program that tabulated the huge list of the separations between top and bottom and center and bottom for every minute along the several hours of the conjunction, and for every observer. So we had to give him our position, and in theory, it's also, the refraction is also affected by things like the air temperature, atmospheric pressure. I'm lucky enough to live next door from Moffett Field, so I can download their weather reports, and I have a good information, even historical information about the weather. But that was not particularly critical. So when you have done everything with the NOVAS program, then you can calculate the expected separations, the top to bottom and the center to bottom expected separation, which I called T minus B subnovas and C minus B subnovas from these topocentric coordinates. And this is a typical chart that you can see when you run the numbers through NOVAS. As you can see, going from 6:30 universal time to 10:30 universal time, the separation between center and the expected separation between center and bottom, this is calculated for my geographical position, changes, and it goes from 410.42 arcseconds to 410.47 arcseconds. So we are talking about a change which is 1 order of magnitude larger than the deflection that we want to measure. So you definitely need to take this into account. And even just figuring this out, what needs to be taken into account and what can be neglected, was not the easiest thing. There were long discussions on the project mailing list. So once you have this data from NOVAS, then you have to start looking at your data, at your images. You have to calculate the centroid positions for the 3 stars, so top, bottom, and the center, expressed in pixels on the sensor plane. And hopefully the pixel matrix has constant pitch throughout the sensor, and so you can use that as a proxy for position. You have to correct the centroid position for the distortion of your imaging train. Again, when you are measuring thousandths of an arcsecond, that is not negligible. It's actually quite, it becomes significant. It's the same order of magnitude as the deflection that you want to measure. Then you can calculate the image scale by dividing the top to center distance, the top to bottom distance from NOVAS and the top to bottom distance that you measure on your sensor after correcting for distortion. And finally, you can calculate based on the image scale and based on the separation between the center star and the bottom stars in number of pixels, you can calculate what you are measuring in terms of distance in arcseconds. I apologize for the mistake. This in the third bullet point is obviously T minus B and not T minus C. I'll fix that. Once you have that, you can subtract the predicted center to bottom distance from NOVAS, and you obtain the deflection. Rinse and repeat for about 4,000 images each hour. and we had the data taking lasted several hours. So there's a lot of need for automation. You cannot possibly do this manually. And so back to Jerry's question, we used a Python program that automated this and was written by Bill Fisher. Interesting thing that we learned in doing this project, we used Howell's algorithm for centroiding, and it's essentially an algorithm that calculates the center of mass of the light distribution, as if the brightness of each pixel were a density of a physical object. Well, we found that centroiding with the center of mass algorithm is very sensitive to the presence of gradients in the background. I actually did a little bit of a simulation, and this is how a certain gradients expressed in ADU per pixel affects produces an offset in the centroid measurement. Note that we're talking here, the endoscale is 60 milliarcseconds. So again, it's 1 order of magnitude bigger than what we are trying to measure. We have to correct for this somehow. So this is what you can expect to see if you draw a line through Jupiter and the star SAO at 93016, and you examine the pixel. This is actually a chart that Nicola sent me. And you can see the star is right in the foot of the gradient from Jupiter. And actually the slope of the gradient changes as throughout the PSF of the star. So we cannot neglect this. Definitely we cannot. How do we do that? So we considered several strategies. We tried to subtract from each image a rotated version of the same image registered on Jupiter's center, which is in itself problematic because Jupiter is saturated. So centroiding on Jupiter is not very precise. Also, Jupiter is not circular. So if you want, we can talk about the radial aspect of this gradient, but it's actually no radius. It depends on the azimuth. And so we should consider a 180-degree rotation, or maybe the average of two smaller rotations, like 20, 30 degrees, or up to 40 degrees. Or we could subtract from each image an image of the planet taken at a different time, like 1 hour after the image that I'm analyzing, or 1 hour before the image that I'm analyzing. We are relying on the fact that the movement of the planet relative to the star was quite fast. So if you are subtracting an image, you're not going to subtract, and you register the image on the planet, you're not going to subtract the star. You're only going to subtract the planet and hopefully the gradient, which hopefully should remain constant. But this is also not entirely true, because there's variations over time of transparency that you cannot really account for, but they were observed. So this is an example of how effective was one of Bill's algorithm. This was you can see on the image that I showed a few slides before. There is the algorithm for gradient reduction was applied in a small box around each of the 3 stars. And this is a zoomed-in version of the image of SAO 93016. It's not perfect, but it's a pretty good correction. Especially, one of the reasons why it's not perfect is that you can subtract the average value, and already it's difficult, but you can never subtract noise. So the parts that have that were originally brighter are also associated with higher noise. And you're going to be stuck with that. There's no way to remove that. So this turned out to be probably the most critical aspect of the project. And we performed many simulations, in particular Don and Bill, to determine what would be an acceptable reduction of the gradients that would lead to a systematic error much less than what we wanted to measure. And we also found, while doing that some optical systems turned out to be more suitable to this than others. For instance, the presence of vanes to support the secondary mirror in an RC or a Newtonian, they cause a loss of radial symmetry. So you cannot do certain types of gradient reduction that involve rotation. They typically don't work for that. And I believe that in the end, Don, you actually, in your final report, I think you used mostly refractors, right? Yeah. So another topic that we found was not possible to neglect was image distortion. So imaging systems at this type, when we are making this type of fine measurement, are not necessarily orthoscopic, which means that the image scale is not uniform across the whole frame. And this distortion needs to be characterized across the field of view of your sensor when you want to convert pixel positions to celestial coordinates with the type of accuracy that we were after, so milliarcseconds. To do this, each of us captured a set of calibration frames. I did it before starting taking data on Jupiter, but it was also possible to do it the day before or the day after, as long as the imaging train remained the same. And you take these reference frames, calibration frames, we call them, around the zenith to reduce the effect, the influence of atmospheric refraction. And we used a program called Astrometrica to characterize their geometrical distortion. Basically, the program, you can instruct it to output the coefficient of a polynomial transformation that maps pixel coordinates into celestial coordinates. This is an example of the graphical representation of the distortion in the field of my telescope. Each of the green vectors represents the intensity of the distortion in that particular point, and each point is one measured star, essentially, by one star that Astrometrica was able to measure. Okay, some examples of the data that we have collected. So these are is the analysis of my 73 gigabytes of data from that night. So I didn't collect from early evening to 2 a.m. because I was constrained by trees, but other people did it. So we, as a combination of observer, were able to track the conjunction for a good number of hours. This is what I observed, and this is the deflection, my deflection error measured. This is a data analysis done by Don versus the time of observation. As you can see, there's a clear effect of seeing on the spread of the measurements. At the beginning of the night, I was having worse seeing, and you see there's almost half an arcsecond plus or minus, and this was going down to probably 0.3 arcsecond plus and minus at the sorry, when the planet crossed the meridian around the time of the closest conjunction. For each of the chunks that we divided the data in, so of about 30 minutes, we measured the mean value of all the calculated deflections, and they are on the mean using the formulas that we saw earlier. And so we got to this kind of results. This, again, is Don's analysis of my data. The blue dots are the average values of the of the deflection in each chunk, in each 30 minutes chunk. The error bars were estimated based on the spread of the measurements. And the orange line is actually the theoretical prediction of what we should have seen using general relativity. So I'm already giving out the killer of this mystery. So when Don analyzed the data from other observers, found that we all observed the same thing. Essentially, this is the overall chart of all of the measurements coming from refractors for the reasons that I explained earlier. Yeah, there is definitely a statistically significant difference from the plot of our observed deflection and the expected curve. They are the shape is so similar. It's tantalizing similar. It's really tempting to say that yeah, we did measure this the deflection. However, the magnitude does not match what the theory predicts, and it's not just we don't think it's a systematic issue, because we tried with different algorithms for glow removal. We actually had 4 in our arsenal, and they all seemed to give offsets at least in the same direction. So regardless of the algorithm that we used to correct, we were always getting a value larger than the theory predicted. This may suggest that there is something else going on, and not that we have discovered that Einstein was wrong, obviously, but that maybe there's a factor that we haven't considered. What could be this factor? Well, as every scientific paper says, more research is needed, but this opportunity, as we did this time, won't repeat itself for a long time, as we said, until the beginning of the next century. However, Dr. Bruns is working on a new campaign with a different method, based on not on the deflection of starlight, but on the deflection of the light coming from Jupiter's moons. Jupiter's moons have orbits that are well known and that can be calculated with a very high degree of accuracy. And so you can hope to measure that, yeah, the satellite Io is not exactly in the position that theory predicts, but is slightly deflected. The advantage of that is that you can repeat the measurement to your heart's content, because as long as Jupiter is visible, you can take measurements every night. And actually, the interesting thing is that in this year and in the next year, the geometric condition for Jupiter will be almost ideal for us observers in the northern hemisphere. Will be very high in the sky, and so the seeing will be less of a problem. Differential refraction will be less of a problem, and we hope that we can get more data. And if anybody is interested in collaborating to this new project, definitely contact Dr. Bruns at dbruns@stellarproducts.com. This will be also in the YouTube video, and so I hope that people will decide to join us in the next project and the next measurements. Thank you.
All righty, thank you very much. So are there other questions from the participants?
This is Jerry again. That's an excellent presentation. I was just wondering, one thing that would, I guess, reassure me also about what you're doing is that if there was some kind of random error that you were measuring, you'd think it wouldn't go in the right direction. So in other words,
yeah,
if you're measuring, like I do a lot of statistics, right? And so what you wind up seeing is that if you've got some real random error coming into a system, it could just go plus or minus, but you're going in the expected direction. And the other thing is that the temporality of it. In other words, it was at the right time. Now, the magnitude might not be correct, but you have it in the right direction and you have it at the right time. So I think that, that speaks a lot for you actually having a valid signal. Although, the history of science is full of artifacts that look really good until people thought about them carefully, and then
confirmation bias is
vanished
always
into dust. But it's very interesting.
Yeah, confirmation bias is a concern, absolutely. And it's true about the random nature that you said, Jerry. This is why we were so worried about the Jupiter's gradient, because that is not random. That's a systematic offset.
Yeah. So, that reminds me of another question I'd like to ask. I've been suffering with some new data which has horrible gradients in it. Not horrible, but bad enough, much worse than what I'm used to. And so I started studying a little bit. When you were putting up those pictures, I was thinking about some videos I have been watching over the weekend about the new gradient removal tools for
Yep.
PixInsight. You know, you have Gray Expert, and you have Gray Exterminator, which is, I guess, older, but another AI one. And then you now have PI's own gradient correction, I guess it's called. And I was looking at what you were doing because I could see you were doing some of the stuff in PixInsight. I was just saying, oh, gee, you wonder whether you could have used one of these tools to try to put a handle on the gradient that you were experiencing with Jupiter, because, you know, these guys have spent a lot of time and trouble working out the math of their add-ons. So if there was a way that you could have harnessed, like particularly the PixInsight process, that might have been a way of, you know, dealing with the gradient. They do work pretty well as far as I can see, but, you know, they're different. And they also have a lot of bells and whistles that you have to, knobs and things to turn along the way. But I was just wondering that, you know, if you get stuck in this position again, whether you would think there might be a way of harnessing some of the internals of PixInsight to go after the gradient.
Well, we have all the data, so if something comes out, we can reanalyze. I think, Donna, you had raised your hand. You wanted to say something.
Yeah, I can mention a couple things. The gradient removal was certainly the toughest thing, and we tried different techniques. Bill Fisher wrote a program, and I also did my own program totally independently, and they still got this gradient problem. So these are customized programs rather than, we considered something like Python or PixInsight or something, but using a custom one was the best we could do. Now, when Jupiter's not there, we actually tested this for a year or so. When Jupiter's far away, looking at these three stars, and I was getting RMSs like 2 milliarc seconds. So I was very hopeful that Jupiter subtraction wouldn't be that bad. And if I got like 5 observers, each of them with a 2 milliarc seconds, I thought I could get this curve down maybe to 1 milliarc second. But Jupiter is just so bright. Now for the moons coming up, you might try methane filter. That darkens Jupiter tremendously, but the moons are still pretty bright. And I'm still debating whether to try that or not. But the moons are so bright anyway that maybe Jupiter's attraction won't be a problem. We'll find out next fall.
So Don, you just mentioned something that I was going to ask. So if you collected the same data without Jupiter, you know, let's say, you know, now collect the same data as you collected that night on those 3 stars at the same time, you know, you think, you know, is it a totally flat line now? Or is there a you know, that could, if there's a systematic there having to do with, I don't know what, the meridian, you know, one could find it without Jupiter, right?
Yeah, we tried this again, either the night before, if it was clear, or a month before. I tried over and over again, and I kept on getting numbers like 0.002 arcseconds. So I was very optimistic, but the gradient removal is just the problem. Now, Francesco hinted maybe there's something else going on in the theory. I still haven't figured out or worked on it, but maybe Jupiter has rings around it, right? Maybe they scattered the data. I'm afraid to say that out loud, but maybe.
You think the rings, the mass of the rings is negligible. Oh, but you're saying it deflects it in
scatters the light or something.
Yeah. More maybe more optical, that in quotes, than gravitational. Yeah. But yeah, it was speaking for myself, it was a very interesting experience. I was very happy also to see that there were other observers from SJAA that joined. I see that we have Nicola here, and he was also in the project, although he was unlucky with weather and equipment. Nicola, do you want to say something about your experience? I don't want to put you on the spot.
Well, Nicola's unmuted, but I guess can't.
Yep,
Somehow
probably.
it's not coming through.
Maybe the mic is not. Yep.
So I assume that this experiment has been done with, professional equipment and verifies the theory well. Is that the case?
No, it's only been done with radio waves and quasars. It's never been done optically. Hubble tried. I talked to the people who used Hubble with like 10th magnitude stars, but their calibrations weren't good enough, so they didn't even bother publishing. So this is a unique experiment, unique opportunity, and again, thank you guys for trying out. I just wish we could have gotten this a little bit better.
All right.
One interesting thing is that although it was not, I think it was you, Don, that in the project mailing list were saying that the data releases from Gaia actually they apply a correction in the astrometrical position for the proximity of the larger planets, right?
Yes, and so does NOVAS. NOVAS program, you can turn off gravity from Jupiter and Saturn or Sun, even the Earth. You can turn it on or off. So it's a very nice program, by the way, even though it's in Fortran.
Yep, and it exists a version in. They also have a version for Python, if somebody wants to use it put off by Fortran.
Okay. All right. So are there any other questions or comments? Either Francesco or Don or somebody else?
Can you hear me now?
Oh, yes.
Yes, we can.
Yeah. So I was unlucky to collect 4,000 images every half an hour. But thanks to the project, I learned a lot about my optics. Basically, how to measure distortions and how to do more accurate measurements. So it's really useful for those who participate, at least to understand their rig and how precision is the setup. Yeah.
Thank you for joining. This is a tough project. There's a lot of little details that I think most of the details of this distortion and refraction and averaging all these things, but at the end we just got it was close. It was close.
It was.
Yeah, it was.
And one of the things that the take-home lessons is that I had already had that experience when I built the light curve for the supernova in M101 last year. But it's amazing how this equipment that we basically play with, they are toys, they are actually scientific instruments and they can be used for scientific measurements if we want. And I'm guilty as charged of giving most of my attention to pretty pictures more than the actual data. But this one was a very interesting change from my imaging routine.
All right. Well, with that, thanks very much. And please, everybody, unmute and give Francesco and Don and Nicola. And thank you. Great job.
Thank you so much. This was very educational.
Thank you.
Thank you.
All right. We'll see everybody next month. Talk to you later.
Thank you. Thank you very much, Don.
Okay, thank you.
Thank you, everybody.